The next approach, the next algorithm in scheduling algorithms is round robin. The round robin algorithm is actually works in the rotation, right? That every process is getting some unit of time, some unit of CPU time, right? We say that it is the quantum time, the time assigned to any CPU burst, any process for its CPU burst is time quantum, is usually represented by Q, small q, right? And usually this time varies between 10 to 100 milliseconds, and this can be even smaller, but if you do smaller, then the efficiency may not be good because of the context switching. If we do some smaller switches, very rapid switches, if this quantum time is small, then there would be rapid switching between the processes. So this time is usually very small. A round robin is actually works on the rotation, where every process is being assigned for a particular amount of time, which is the time quantum. Okay, so if there are n number of jobs, then maximum quantum time will not grow than this, right? N minus 1 q, right? So actually, if we see round robin, that for suppose there are maybe if I say that process like this is a cyclic, right? And these are some jobs. Okay, and here is the CPU rotation. So CPU first started from this, and then to this, then to this, it goes like that. And again, when it reaches to this, then again it goes to the first process. So it means that when if we see this in the queue order, if we see this in the queue order, then you take the first job, perform some operation on this. This is CPU and this is queue, right? If you take this job and perform some operation, then there might be some other jobs also waiting, and then when you this quantum, let's say this job is in this algorithm, if we consider it is being assigned to the CPU for 10 milliseconds, then after 10 milliseconds this job is pushed on the back of this queue, and it has to wait for maybe if there are 10 jobs, then it might have to wait for 100 milliseconds to get the next turn of 10 milliseconds. Okay, and this quantum must be larger with respect to context switch, otherwise the overhead is too high. For example, if the job is maybe for 50 quantums, and we say for the 10 quantum, every job will be served every time when it gets its turn, then it has to do only 5 context switching. But if we say for the 50 jobs, if we have 5 milliseconds, then it has to do 10 context switching. So context switch is also, as we have seen in the dispatcher, that context switch takes some time. We have dispatcher latency, so to minimize that latency, we have to assign the a very generous number for this process to apply, right? To this process for performance of this process, for performance of this the CPU over the CPU. Okay. So if we come here, the example of round robin, then for suppose that P1 is of length 24 and P2 of 3 and P3 is complete CPU time first. Okay, and the quantum for this may be 4 seconds. Q, where Q is 4 seconds, right? The quantum for this round robin is only 4 seconds. So when P1 was right, it was served for 4 seconds, then P2 was served for 3 seconds because it is less than the quantum, so it was completed. Then P3, then again P3, when the P2 has arrived, which is for 3 seconds, CPU bus, which requires CPU bus time only 3 seconds. Then P3 is there, which also requires CPU bus for 3 seconds, and then again the turn comes for P1, and again P1, again P1, 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 okay, until the P1 is completed. So at 30 unit of time it is completed. Okay, so usually it returns higher average and then the shortest job first, but the response time is better here because every job is progressing, every process is progressing, so the first response is better in here. In many applications we need this approach because where you want to progress, at least the process should progress, it should not be stopped. It's like that if you are you go to some maybe at a photocopier, then someone has to do some photocopy of 500 pages, another has to do 200 pages, another has to do 5 pages, and so different number of pages guys has to do photocopy, and there is only one photocopier machine, so everybody will be given some amount of time so that everyone should be satisfied. Okay, that okay, they are progressing. Okay, and here if we see that a process is time units maybe 10 seconds, right, and the quantum time is 12, then there is no context switching. But if the same process with quantum we perform with 6 quantum time, then there is one context switching. But if we have the quantum length of 1, then we have to fall into many number of context switches. So we have to do 9 times context switching from one process to another process. We have to switch between the processes for 9 times to complete this job. So whenever we are implementing this algorithm, we should make sure that the context switching time that should be the minimal and appropriate time. Okay, and this has actually great effect on also turnaround time. Now next comes the priority scheduling. Before going to do that, I must also tell you that if the P1, if I suppose if 2 jobs arise and both jobs are equal, then the context switching will be done in FIFO. Okay, first FIFO or first come first serve, right? And the priority scheduling, in priority scheduling, every job, as in priority scheduling, actually there are several applications where one job is prioritized over another job. Okay, for suppose in real example, if you are waiting on the university cafeteria, right? Here is a cafeteria counter and a guy is sitting over here who is serving the customers, university cafeteria. Now These are students. Suppose these are students. Okay. Suppose a teacher has arrived, right? A big fat man guy, right? Guy has arrived here. Now this guy will be given priority, maybe teacher, right? Right. This guy will be given priority over these students. Okay. So that suppose this student is being served, then there are two approaches. Either this guy, the server, leave to serve this, stop to serve this student and start serving this, because this is teacher, it has priority, higher priority, and this might have lower priority, right? I'm sorry, 2 and 3 and 4, right? So this guy has higher priority, and in respect of this guy, this teacher, this guy might stop serving the student who has priority 2, and suppose one after another the teachers arrives, right? One after another, maybe the teachers arrives, and these guys maybe are pushed on the back, because teachers are arriving, keep on arriving. Now this guy is starving, and he's not getting his time, he's not getting his meal. So these guys are actually starving. In priority queue, starving means that lowest priority process may never execute, or may take longer to execute. Okay. The solution to this is aging. Solution to this is aging. Aging means that every time when you are serving, every time the one who has, every time the remaining jobs are incremented by one. Okay, maybe typically the smaller the integer is the highest priority. For suppose if we compare between 1 and 10, then 1 is the highest priority, 10 is the lowest priority. Now for suppose the 1 is being served, then the 10 would be minus by 1, right? And now the priority of this guy is 9. At some instance of time, this guy will get the priority of 1, and it will be served first. So to promote the remaining processes, the priority is increased. This is actually an increment of the process, right? However, when you are programming, the priority is inverse of that concept. When we are talking about the conceptually, the 1 is the highest and 10 is the lowest priority. But when we are doing some program, if you go into the Java and maybe another working, then the 1 is the lowest priority and 10 is the highest priority. Okay, so starving means when the lowest priority job has to wait forever, or maybe wait for longer, and aging is solution to that when, and they are being promoted one by one by increasing their priority in every turn. Okay. Now here if we see that process 1, process 2, process 3, process 4, process 5, here we don't consider the CPU burst time. Here we consider this priority. Now priority, when you are programming, you might have already done in your Java course, whenever you set the priority, whenever you are programming, you set the priority of a process to execute. Maybe you have seen in data structure course where you have studied different type of queues, right? So in this, the priority matters, not the CPU burst time. So this guy has P2 has priority 1, then P5, then P1, then P3, then P4. You see P2, P5, P1, P3 and P4. This arrangement is on the basis of priority. So average wait time, if we add this wait time, maybe later on you can add the arrival time also, which may have a big impact on this average wait time. But in just if we are not considering arrival time, then we would say that the average wait time is 8.2 milliseconds. So the arrival time is excluded in this average. If we add arrival time, then this might be minimized. Okay, might be minimized, not sure. Okay, and then priority scheduling with round robin. Similarly, we have same jobs. Run the priority high process with the highest priority, process with the same priority runs the round robin, right? So the highest priority is P4, right? The highest priority is P4, and this P4 will execute first. This P4 execute first for 7 units of time, and then this guy, this guy, this guy, and this guy, whatever the priorities are there. Now if these two have the same priority and they are remaining, then they will be served alternatively, right? So then P2 come, P2 come, and then P3 come, P2 come, P3, P2, P3, P1, P5, P1, P5, okay? Because these two have same priority and these two guys have same priority, okay? So actually we have different type of queues managed for different priorities. We'll see in the next session that how the same priority as we see, this is also same priority and this is also same priority. So how this is actually managed in operating system. So for managing this condition, we have multi-level queues, which means that for priority 0, all guys belongs to priority 0 goes here, priority 0 is highest here, and theoretically, and priority 1 is lower than that, priority 2 and priority 3. So all so these queues are on the basis of priority. All P0 processes fall in, goes into this level and into this queue and into another queue, another queue, right? So it's this is Q1, maybe Q2, maybe Q3, and maybe Qn, right? For priority n, we have Qn here. So every priority has its specified value. So first of all, this queue will execute, then this execute, then this, and so on up to this. Right? One by one will be executing these priority queues. So the same thing is happening here. So first we give time to maximum the highest priority job, and then we switched between the second queue, and then we switch between the third queue here, right? This prioritize may be based upon the type of the process, as I have already told you that size and type matters. So this actually based on the type of the process. If it's real-time process, then it has highest priority. If it's system process, then it is lower than that. So real-time process has the highest priority, then this, and then this, and then this the lowest priority is page process. Page process, why it's lower? Because it's longer in size. Usually page processes in servers are longer in size, okay, size, and maybe different types, right? So so these two parameters are actually considered in this multi-level queue. However, here it is mentioned only type, but the size also is the consideration parameter when we are dealing with the priorities. Then we have also multi-level feedback queues when a process can move in between queues, different priority queues, in between different priority queues, which means that, for example, we have multiple number of queues, and a job, if completed in Q1, then it's fine. If not completed, then it will go to Q2, and then it will go to Q3, right? So the movement of jobs in between the queues is also possible, and this is sometimes, if this movement is happening for not only the queues but also the processors or CPU cores, then it is called as a migration. Okay, migration in between the CPUs and the queues. For example, if I tell you that there are multiple queues, okay, here CPU which belongs to these three, another CPU belongs to these two, another CPU belongs to these two. Okay, so maybe a job is working in this, right? And then it moves to this queue, right? And then it moves to this queue. Is migration within the core, so it doesn't matter. But it is also possible to migrate from one processor to another processor, the queue of one processor to another processor. It is also possible. So this is actually migration. And then this movement, and when if this job is not completed, it is moved over here, and if not completed, it's moved over here, is called as feedback queues, right? Feedback queues. So it's written here, right? Feedback queues. So if we see here, that first suppose we have three queues, and one is the first one is round robin. This is round robin. This is also round robin, and this is first come first serve, right? And this has quantum time of 8 seconds, and this is 16 seconds. I'm just considering seconds, it can be milliseconds also, but milliseconds is longer word, so I'm using some other seconds. Okay, so if this has to, first suppose a job has arrived, it is for 30 seconds. Okay, then Q1, this is, let's say, Q1, this is Q2, and this is Q3. So Q1 and Q2 and Q3. So for in Q1, it has got 8 quantum of time, and in Q2 it has got 16 quantum of time, while in Q3 8 and 16 it's 24, and for 30 seconds it's get 6 seconds over here in first come first. So in round robin it can only complete for 8 unit of time. In Q2 round robin it can complete for 16 unit of time. The remaining will go to the first come first serve. Here if we see a job right here with 30 seconds, and if completed it goes to terminate, right? I mean to next phase. If not, then it is pushed back to another queue, and where it will be served for 16 seconds. If it is completed, then well. If not, then we'll go travel to the next queue, first come first serve. Then if it's complete, it's okay, right? And it has to complete over here. So this can be a preemptive or non-preemptive again. Usually non-preemptive, right? Usually non-preemptive. Okay, this tutorial is all about that same thing. So the contention and the thread scheduling. In thread scheduling, most modern operating system kernels implements the kernel level thread. Kernel level thread means that it's not, they don't say it's process, it's actually thread. On kernel level it's thread, not the process. Okay, it is scheduled by operating system, And the user level thread, ultimately the user level threads are actually mapped into the kernel level threads, as we have already seen in our previous chapter, chapter 4, that we have many approaches, one to one, we have many to many, right, approach. Also we have also many to one approach, right? So we have different approaches of threading, right? These are this is the user level and this is the kernel level. So this mapping is actually happen in between user and kernel level thread. So a user level thread is ultimately going into the kernel level thread. So when we are talking about scheduling, we most of the time we are considering this portion, the kernel level threading, right? And many to one are many to many models, thread library levels on the low weight processes. Okay, so we will see the contention scope. Contention scope. Whatever this scheduling I have told applies also threads, because I have already told you that thread is actually a process, right? In modern operating system, it's not process, it's actually thread. Because every process, every application, every process we perform has several threads nowadays. So the same approaches also goes with the threads. And the contention scope is contention basically actually the meaning of contention is a computation state, right? A garma garmi ki situation. So the contention is the computation scope of the processes. Now there are two type of contentions. Okay, the first one is the process contention, when the same process, when the threads which belongs to same has the same priority, and there is a contention between them, there is a computation between them. And when there is another computation is over the system level here, where different processes has computation in between them. Okay, so all of the threads of all of the processes are actually computing. So this is these two terms are with the thread scheduling. However, the approaches are same as previous. If we see some scopes here, the programming related, then when you are dealing with the process contention scopes, you call it as Pthread. In Pthread scheduling, it's Pthread scope process. And whenever it is system contention scope, then Pthread scope system. Okay, in the example, this is the same example which we have seen in previous. Only the thing which is changed is here that the what is the process? It's what is the contention scope? And the contention scope is process. Our contention scope is system. So we are just printing this here. Okay, but this is the same, the sum of the variable scenario. Okay, the same example over here. Okay, and whatever the threads were created are forked and they are joined back. This is the same example which we have seen in previous chapter. Then we have also multiprocessor scheduling. The multiprocessor scheduling actually involves when we have multiple CPUs or maybe multiple CPU cores for scheduling. Until now, we were considering that there's one CPU, but it is also possible that we have. It is usually it's most of the time it is possible. It is the condition in real systems that we have multiple CPUs where we have to allocate the jobs. So how these CPUs are actually dealt? Okay, how this scheduling is actually done in these different in these multiple processors. In multiple processors, we might have multi-core CPUs where one CPU, one CPU has maybe 1 core, 2 core, 3 core, and 4 core, quad core, right? And we can also have multi-threaded cores, which means that each thread can run multi-threads at a time, right? Maybe 2 threads at a time. And we have also non-uniform this memory access, right? Where the memory access is maybe every CPU core has a queue, a cache here, right? A queue or cache or memory portion assigned to them. And the non-uniform access is actually access in between these queues. Maybe this core is accessing the memory of this core or this core or this core. So this is a non-uniform manner of accessing the memory. So non-uniform memory access systems also there. The heterogeneous systems, when here we have same cores, right? They have same capabilities of performance, right? But we can have also heterogeneous systems where the things are different. Means we might have a system here, right? Maybe dual core. Another system is quad core, right? So we can have heterogeneous type of systems. Or maybe this is dual core, another is also dual core, but the memory is low, right? Memory is low here, memory is large. Okay, so we might have different type of systems. Another condition is also here, which might be covered in multicore, but it is good to tell you that there is also homogeneous processors. This is an ideal situation. It's not real that two processors with exactly same configuration, but it is not considered because even same configuration doesn't respond to you in the same manner exactly in the same time. So the response can be different. So homogeneous processors can also be there, but it is an ideal situation, not the real situation. Okay. So the first one is when we have multi-core systems. There are two things that in multi-core systems we have common queue, and we have some specific queue. Every core has its own queue, and every core is accessing to the same queue. Okay, now this is a system and it is working on the same queue. Everybody is accessing to this queue only, right? While in here we have different queues for this system, right? We have different queues. This system has this queue, this system is this queue, and this is this queue. So every core has a different queue, and we have to balance between these queues. Now there's another thing in multi-core operating system and multi-core processors, that there is a memory stall. Okay, a memory stall is actually a waiting for a place to wait for the data to become available. Okay, and reason is that the reason for this may be processors are fast and memory is slow. So the process has to wait for some data to bring it in cache, okay, to bring it to near the CPU. Okay, so the one main reason is that processors are fast and the memory is slow. While another thing is cache miss. Cache miss means that data missing from the cache, and the processor is trying to access some data from the cache, but the data is not available in the cache. So mostly the memory problems, due to memory problems, we have a memory stall here. Memory stall means where the CPU wait for some memory input, okay, some input from memory. So this is mostly done into the cycle, where compute and memory. These are two things which works in the cycle like round robin, right? It's not round robin, but these two actually work in the cycle. Don't say it's round robin, I just said mistakenly. But so you can say that this is a compute state, and then again it goes to the memory star for some data, and then again when it gets the data, it computes something, and then again memory star compute, and memory star compute, and memory star. So one after another, the state goes like that in the cycle. Now, the scheduling is the beauty of scheduling is to actually manage this this memory time. Actually, if we I have in the very start of this lecture, I told you that there's CPU burst and there's IO burst, right? When so CPU burst, if we say this is IO burst, this is CPU burst, this is IO burst, this is CPU burst, this is IO burst, this is CPU burst. So what we have to do, we have to actually maximize the utilization of a processor by utilizing the idle time. Like that means when a process is waiting for the memory, when the another process is working, is occupying the computational resources. So we see here, for suppose in a multi-core multi-threaded systems, we in a single CPU, we for suppose if there is a single CPU and it is multi-threaded, means it can run two threads, right? So they are managed like that when it is computing, when it is computing, it is this thread 0 is waiting for the memory input, and when this is waiting for memory input, this is computing, this is, so you can see that this is time, right? This is time. Now this time is being utilized, this time, this idle time is being utilized by this. Similarly, this idle time is utilized by this. So we have to utilize the idle time in that's why the multi-threading technology was introduced in the latest processors. If you see the i7, i3 or i5 processors are multi-thread, right? Are also high in Microsoft and Intel also call it as hyper-threading, right? Hyper-threading technology, right? Intel has this hyper-threading technology. Whenever you go for some for purchasing a computer, then when you say I need i3, I need i5, I need i7 computer, or maybe nowadays there's i9 computer. So that's actually maybe quad core and i9, right? Maybe octa core i9. Then this is the fastest computer. Okay, you have 8 cores and you have some threading technologies, right? So hyper-threading is actually multi-threading technology. Now multi-threaded and multi-core systems are actually like this, and the processor maybe have 4 cores. You can see this is a processor. It has core 0, core 1, core 2, core and core 3, right? It means 4 cores, and each core has 2 hardware threads, right? 2 threading. It is capable to deal with the 2 threads. Now virtually this operating system see this as that every thread is dealt actually as a CPU. So virtually, or maybe the operating system view to these threads is not as a core, but not as a thread, but as a core. Okay, core CPU. So if this processor has 4 cores but 8 threads technology, then and the CPU, the operating system see this processor as 8 core. Okay, we have also 2 levels of threads. The operation system deciding which software thread to run on the logical CPU, and which process and how each core decide which hardware thread to run on physical core. Now this is actually the operating system view, the soft thread, and this is actually the hard thread. Now we have to balance the load. I have already told you that to avoid the overburden of any processor, we need to balance the load in between the processors. Now this balance requires the migration. For example, if we have maybe this queue here, this queue here, this queue here, this queue here. Now we have a quad core computer. This is CPU 0, this is CPU 1, this is CPU 2, this is CPU 3, and maybe this is occupied, right, and this is occupied until here, okay, and this is occupied until here, and this is empty, so this is idle. So we are not balanced here. The processors are not balanced. They are not implementing the fair policy to balance the load in between the processors, in between the CPU cores, or in between the cores. So there's a technique of migration. Now, for suppose in this process, if we push it here, or maybe if we push it here, then this is push migration, okay. But if this processor, this core, see that I'm idle and I need a job, then it will pull a job from here, right? This is called pull migration. So we have push migration and we have also pull migration, okay. So periodically tasks check the load of each processor. If found someone available, then pushes the task from overloaded CPU to another CPU, okay. And pull migration, the idle processors pull the waiting task from busy processors, okay. So these two are concepts, the push migration and the pull migration, to achieve the load balancing, okay. Now there's another thing which is called affinity, okay. Affinity is actually bonding memory and threads to a particular CPU or particular process to avoid migration. Because whenever a process is migrating from one queue to another queue, it is actually doing some context switching. It is actually losing the data in existing queue, and it is again getting that data in the new queue. So this migration is usually avoided because it has large losses. It loses the data, and it travel to another queue, right? So there are two type of affinities. The first one is soft affinity, and another one is hard affinity. Soft affinity, a processor or operating system tries to keep a thread running on the same processor, but it does not guarantee. Another affinity type is hard affinity, where a processor does not allow a process to migrate in between to another processor, to another queue, right? This is hard affinity. So allows a process to only work on a specified set of processors it may run, right? For a set of processors, or maybe a processor, set of processor in terms when they have shared queue. For example, these there are 4 cores. This says it's queue, this says its own queue, while these two has a shared queue. So this queue might have these two processors, okay. So a process in hard affinity is only bounded to remain in these two cores, not in these. If while in soft affinity a process is bounded to operate on these processors, but it can also migrate to another process. No guarantee. Okay, no guarantee. It can migrate. While here it is guaranteed. Okay. Then we have non-uniform memory access and CPU scheduling. In non-uniform memory access, for suppose a CPU, there are two CPU cores. CPU1, maybe this is CPU1 and this is CPU2. Let's see. And this is CPU1 and this is CPU2. Now when this access from the memory allocated to this process, maybe cache, right, cache of this process, then this access is very fast. While when it access from another cache, another CPU's cache, then this access is slower, right? So this is a problem with non-uniform memory access. We have also real-time systems, very critical and very important systems. As I have already told you that maybe we can say that medical systems are time critical systems. They need to finish the task within the deadline. There is a deadline defined for a task to finish, and the task must finish on that deadline. So there are two types of real-time CPU scheduling: the soft real-time systems and the hard real-time system. The soft real-time systems are systems where the CPU tries to perform the jobs with priority, but it does not guarantee, because maybe it's implementing maybe the aging factor, the starving and aging factor may involve. And also there's hard real-time systems where the priority queue is actually maybe rearranged in first come first serve basis, or maybe a priority basis, that the highest priority would be performed in non-preemptive fashion, in non-preemptive approach. With non-preemptive approach means non-interruptible, means if there is something in smart vehicle environment, if we see that there are two vehicles, they are about to collapse, and these two vehicles has to brake. So this is a hard real-time system, that if this doesn't happen, then an accident will occur. To avoid that accident, every process should be paused for some time, and this process should be attended. So this requires hard real-time systems, hard real-time priority, hard real-time scheduling. Okay, so real-time CPU scheduling is also an important when we are dealing with the operating systems. And there's a latency. Two type of latencies affect the performance: the interrupt latency and the dispatch latency. The interrupt latency is actually when the interrupt has occurred, and dispatch latency and how long it takes to dispatch to start to submit the process. Next slide we see here the example that, for suppose maybe a task T1 is running over here, and another task T2 has interrupted. T2 has interrupted, that determine interrupt type. It takes some time, right? And context switch, where it save T1 to PCB1. Okay, this is the context switching time, and this is also a time, right? 22, 21. Okay, and then once it is finished and then the interrupt service routine, ISR, interrupt service routine. Then this interrupt service routine starts. So the time, this is called the interrupt latency. However, the dispatch latency we have already seen. We already seen in the previous lecture of this chapter. Okay. Now this is here. You can see also the dispatch latency. The example of dispatch latency. Okay. Now here this is the dispatch latency. An interrupt has arrived, and some conflicts may be need to resolve, and the dispatch time, and then real time execution. So this latency is actually the dispatch latency. Okay. And then we have also periodic scheduling, right? Periodic scheduling means that every there are number of periods. Process have new characteristics, like periodic once require CPU at the constant interval. Okay. So schedule must support preemptive and priority-based scheduling. Again, this is the soft real-time system. It is not hard real-time system, and it is only guarantees the soft real-time system, not applicable to hard real-time systems. Periodic means that a particular amount of time is actually associated with this. A particular amount of this time is actually associated for this process, right, to happen. Now, if this is periodic, then the rate is monotonic. Means that a priority is assigned based on the inverse of its priority, and shorter periodic, the higher priority. Okay, and longer periods for the lower priority. So here are the deadlines. So P1 must be completed by, let's say, this is time unit, and let's say 50 seconds. Okay, and while P1 and P2 should complete up to 100, the first period, there are maybe P1, 2, 3 and 4, maybe 4 periods of P1. The first period should be completed up to 50 seconds, the second period should be completed up to 100 seconds, and the third period should be completed up to 150 seconds, and the fourth period should be completed up to 200 seconds. So similarly for P2, 1, 2 and 3, right? And so I'm sorry, my computer has low power. So we have different deadlines. We can see that P1, P2 and P3. Now approaching to this deadline, this has already completed one period, and approaching to here, and the P1 and P2 periods both are already completed, and approaching to here, and this P1 and P2 periods are already complete. P1 is already completed, and this is also already completed. So this arrow actually represents the deadline, that, and this process should be completed up to here. The P1 should be, the first period of P1 should be completed up to here, and the second period of P1 and P2 should be completed here, and the third period of P1 and P2 should be completed here, while the fourth one should be completed over here. Okay, so periods are actually chunks of the priority processes. Now there are conditions when this deadline is missed. Now for suppose up to here, the P1 should be completed, the deadline. Well, we can see that P1 is already completed around 20, and if we we check at 50, it is already completed. Now up to here, up to 80, up to 80, P2 should be completed, right? Up to 80, P2 should be completed, but P2 was completed at 85. It means that we missed that deadline. Okay, we missed the deadline. So this is what we call missed deadline. Okay, and then earliest deadline first. It means that the process which has the earliest deadline would go first. Now P1, and then we have P2, then P2 will be served here, then P1, then P1 will be served here. Now we can see that we are completing before the deadlines. Okay, so earliest deadline goes first. Okay, also we have shared that this actually results in that if there are T shares allocated among all the processes in the system, then an application receives n shares where n is less than 1. It means that it is satisfactory. Okay, now we have some examples. We have POSIX operating system, POSIX real-time systems, and here's the example of POSIX real-time system, and then we have sorry, this is an example of POSIX real-time system. This is actually same we dealt with in previous chapter. We have seen the example of POSIX, the same example, but the order is the different. The deadline, the priority is different right here. So you can see the policy. Policy, we say policy means actually the algorithm. When we talk about the policy in the scheduling, we are talking about the algorithms. Maybe first come first serve, maybe round robin, or maybe some other priority algorithms goes over here. Okay, so policies actually the algorithms, scheduling algorithm, talking about the scheduling algorithm. So now we'll be seeing the examples of the scheduling. We will be considering 3 different operating systems as the trend goes with this course: Linux scheduling, Windows scheduling, and Sun Services scheduling. Now in Linux, in this book we have different version of this CPU schedulings, and different changes are explained here, but we'll be going to consider only the latest scheduling algorithms. So this is completely fair scheduling, and this is actually a balanced tree whose key is to is runtime. Okay, and the lowest runtime goes has the highest priority, while the highest runtime has the lowest priority, and this works in a tree, right? So we can see here. Okay, this is actually it is mentioned that, and this has the smallest runtime, this has the largest runtime. So this is the highest priority, and this is the lowest priority. Okay, so it goes, every job arrive, it goes either here or here. Okay, every job arrives goes into the tree shape, right, in this tree. Okay, and so this is the CFS in Linux, and also we have real-time and non-real-time system, where real-time systems has the highest priority and non-real-time systems has the lowest priority. Okay, we can see that if this is maybe even the time is 100 to 99 and 100 to 39, so the normal priority system has to wait for longer. Okay, so this is the priority actually, and then also supports the load balancing, as we have seen, but also a non-uniform memory access. So let's consider that a process can access a processor can access some data from even different memories, different cores, the memory of cache of different cores. Okay, and also in Windows scheduling we have 32 levels of scheduling of priority. In Windows we have 32 levels of priority, where 1 to 15 are variable classes. Variable classes, you can say the normal priority goes here if we see in the Linux terms, while 16 to 31 are time critical systems, time critical processes. Okay, so there are 32 levels of priority. Here's to set the priority, how to set the priority, and to see the priority. All of these are the attributes to access them in Windows systems. Okay, this is also an example, and you can see some critical priorities, where you can see that every priority is in between 1 to 31. The time critical system have highest priority. Okay, one thing I must tell you, that now when we are talking, that was in theory, when we say highest priority we say 1, and when it's the lowest priority, let's say it's 30. But when you are working with this programming, okay, then you set the priority in inverse order. This 31 is the time critical system. It has the highest priority, real time system, and then high priority is 15, right? It is not real time, but it is still higher. And so the order is different. 1 is when it's idle, and 31 is when it's the time critical system. So you know that this is the lowest priority and this is the highest priority. However, when we say in theory, then 1 is the highest and 31 is the lowest. But when we come to the implementation, we say that 1 is the lowest and 31 is the highest. Okay. So as the number goes up, the priority goes up. Okay, in Sun Solars we have 6 levels, 6 classes of the scheduling, priority scheduling, right? Time sharing and interactive real-time systems, and also systems fair, share, and fixed priorities. So we have different type of priorities in Sun Solars also, and here the priorities are shown. Okay, and okay, this is a very example. Now we have evaluation method. We have evaluation method. We have deterministic evaluation. We need to do deterministic evaluation, where we can analyze. This is actually about the analysis of system, evaluation of a system. Whenever you are implementing some system, or maybe some new process, or maybe some operating system you are implementing, there, how would you evaluate your system before implementation? Why not implementation? Because implementation is costly. So we need to do some analytical work here, and for analytical work, through analytical work we can monitor, we can see, we can extract the quality of service parameters and the performance, and we can estimate that approximate the performance of a system when it will be developed on a scheme. Okay, so to evaluate your schemes in operating system, we have different type of approaches. The deterministic approach is to determine that, for example, if we have a job which is required to run, okay, then how long it will take. For example, if that job goes into, for example, there are maybe 5 jobs, right? P1, P2, P3, P4, P5 jobs, and the average average wait time for those jobs in first come first queue is 28 milliseconds, and while it's non-preemptive SFJ, shortest job first actually SJ is 13 milliseconds, and in round robin it is 23 milliseconds. So to determine these, we have some approach. We have a queuing theory, queuing modeling. Okay, queuing modeling. The queue modeling is actually a very simple approach. There are actually, besides queue modeling, we have also another approach. Many approaches, but okay, don't make the things complicated. We keep it simple. For this course, we have queue modeling. Okay, so in queue modeling, we have a queue, and we have a server here, right? And we have some jobs arriving in this queue. Okay, these are in connection, and then a job is dispatching here. Okay, so the jobs arriving, and the queue, okay, and the CPU, most usually represented by me. Okay, now this queue here, the time spent in here is wait time. The length of this queue is maybe n, and the CPU service time is represented by me. Okay. Now there is a little formula. Actually, before going to that, for queuing models, I tell you that queuing model is not only applicable for operating systems, but it is actually an approach to model or analyze any system. For example, if you go into your bank, then if you are maybe launching a business, okay, business maybe a supermarket business, this is actually the discussion now is of this course, but when it comes to queuing model, I want to give you some overview that what are the other examples, other usefulness of queuing modeling. Okay, it's not only the modeling for operating system, but it can model any system where queues are involved. For example, in supermarkets, we go and we do some shoppings, right? We get a lot of chunks here, right? And we have some counters. Maybe counter 1, counter 2, and counter 3, right? Several counters. Now everybody finish its job, we come to this counter, right? And here's the queues, right? So we can also use this to optimize that how many counters we will be using. For example, if we maybe 5,000 customers visit per day, then how many counters we need? Okay, so for this type of modeling, we can also use queuing modeling. Okay, also if you go into a bank, right, then again we have some service counters and some queues where people wait, and to provide the satisfactory quality of service to your customer, you need how many counters you need, how many number of counters you need to satisfy the customers, the visiting customers, the number of visiting customers. Okay, so because these are customers, you have to respond them timely, you have to attend them very quickly. So how many counters you need to attend them? In many supermarkets or in many banks in abroad, when you go and you see that they have longer queues, longer jobs, and the shorter jobs, both have different queues. Okay, so when for example, if you have purchased only 2 things from a shop, then you might have to wait for the guy who maybe 5 guys who have purchased the chunk of food with them. Maybe the monthly groceries, they purchase monthly groceries. Okay, and when I was visiting the store, I have only purchased the bread and eggs. Okay, and another guy with big family might have purchased a huge number of stuff with them. So to attain the smallest, the customer who has small number of items, they have automated machines also, that they don't need to wait. They can automatically scan the codes and pay over there and leave the store. This actually satisfies the customers with the small shopkeep, and the one who has big junk with him, he can wait for long. Okay, he can still wait for other guys who have big junk. because he is also keeping some others to wait, so he can sacrifice for that. While the one who has a small number of items, he will not come again if he has to wait for 1 hour for only purchasing egg and bread. Okay, so that guy will not come again. So in many supermarkets, people have implemented the automated machines where they can check out. Also in banking sectors, if we go, then there are several self-service counters where you can maybe resolve the issues by yourself. Okay. The key, there's a farm Little's law. Sorry, there's a Little's law, right? Maybe a formula here. This is the Little's formula, right? This Little's formula, which is actually used to estimate these quality of service parameters. Okay, now for example, here is the queue and the server is departing. Okay, this is arrival and this is terminating, and this is CPU and this is queue. Okay, now the arrival is represented by lambda and the length is represented by n. Okay, and so length is represented by n, while this wait from here to here is represented by w. Okay, now if you want to see the length here, then you have to multiply the arrival with the wait time, and you will get the current length of the queue. While if you need on that how much wait is required, how much wait really a job waits a job in the queue, then you will do in this wait equals to n by lambda. Okay, for example, if you have 14 jobs in the queue and the arrival frequency is 7, then 2 second wait is average wait time. Okay, average wait time. Okay, also represented with W. Okay, maybe somewhere you see W Q, wait Q, the wait time in the Q1 maybe Q2 maybe Q3, something like that, right? So somewhere, if there are no complicated calculations, then you can also see this wait Q. Sometimes this is weight of the queue and this W is weight of the system, overall system. Maybe there are one after another queues, so for weight you have different queues. Okay, Q1, Q2, Q3 and so on, and weight is overall system weight. So to simulate this, we have some in this queuing modeling is actually a simulation approach. We don't need to allocate the resources, and we can simulate them. To simulate, the program model of computer is used where clock is a variable, and the states of these performance indices are calculated using the Little's formula, and the arrival of job generator is maybe a random, or there are different distributions. Sometimes it's bus distribution, it's exponential arrival, or maybe deterministic distributions. So there are several distributions of arrival of jobs. Okay, which can be mathematically defined. Okay, so this is actually the architecture for the simulation. The actual processes and CPUs, IO, CPU, IO, format, time, it will take trace steps. Okay, now the implementation. In the implementation, we actually implement to see that how much time it has taken, how much utilization, CPU utilization was there. But the implementation is not usually done because it is higher in cost, and the environments may vary, so the estimation may not be the estimation may be good, but the cost is higher and risk is higher, because if we implemented some system and it doesn't work, then whatever cost we have implemented on that, it's wasted. So we usually grow people before implementing an operating system or before implementing any system tries to simulate that, okay, their system. And implementation, once they are satisfied with their approach, then they go to the implementation. Okay, yeah, there's another thing that if you have already something implemented and now you have simulated and implemented some new methodology to check the environments, we usually launch the beta versions. Okay, this is another thing. So this is the end of chapter, and in this chapter we have seen the basic concepts of operating systems, where we see what is CPU burst, what is IO burst, and then we go into the scheduler and that how tasks are allocated to the processors, and then we see dispatcher, where the transfer of control in between processor and the process was dispatched. And then we've seen the scheduling criteria. We discussed queues parameters here, quantity of service parameters, where CPU utilization and throughput was aimed to maximize, and the turnaround time, waiting time, and the response time was aimed to minimize. Then we discussed some algorithms. First come, first served, we discussed shortest job first, we discussed round robin, we discussed from the priorities. Okay, and we also, in the priorities, we discussed multi-level queuing. In multi-level queuing, there is also multi-level feedback queues. Multi-level queues means that the different priorities jobs with different priorities are arranged in different queues. Okay, also there is a feedback queue where one job is not completed in one queue, then it travel to the stop and travel to another queue, another queue, another queue, like this. This is the feedback queue. Then we have seen thread scheduling, where we see the Pthread scheduling in the kernel level. Okay. In kernel level, because all the user level threads are ultimately mapped into the kernel level. Okay. And then we have seen the multiprocessor scheduling, and we consider ideal processors, where the processors may not be the cores, but homogeneous processors, which is the ideal situation, which is not realistic situation. We have also two different processes, the heterogeneous processes of different systems. Maybe heterogeneous systems means totally different systems, totally different architectures. One is Mac, another is Windows, another is Windows. Okay, so all operating systems have different architecture, so the systems are actually heterogeneous. And then we have seen the multicores processor, multicore processors, where one CPU has multiple cores, maybe 2 or 3 or 4 cores. Okay, 2 or 4 cores, or maybe 8 cores, or maybe 16 cores. Okay. And also we have seen multithreaded, where each core of a CPU has multiple threads, virtually operating to these multiple threads. Operating system actually sees them like a core. Okay, so if a system is quad core, and each core has 2 hardware threads, then it means that operating system is seeing those hardware cores as an individual CPU, because it is dealing them like a CPU. Okay, like a core. Okay, and we have seen real-time scheduling, and the systems are time critical, highest priority systems. Okay, and then we have seen examples: Linux, Windows, and Solaris examples. CSC and Windows with 32 levels of priorities, and Solaris with 16 levels of priorities. 16 categories, but the priorities are unlimited actually. So yeah, there are 16 categories, but the priorities are unlimited. And we have seen the evolution algorithms, where in deterministic we have seen the queuing modeling, and we discussed the reference law, which is used to extract the quality of service parameters like wait time and utilizations and etc. Okay, and we have seen why we adopt a simulation, because we want to save our resources and we have to estimate the system before its implementation. So why not implementation? Because it's costly, it is high risk, and due to area of environment we have to do a lot of work. So before doing that, we first simulate and then confirm that okay, then decide that it's okay to implement this system, or it is not performing as our expectation, then we will improve on the simulations. Once we are done with the simulation and we satisfied with the performance, then we go to the implementation of operating systems. So the approach to simulate, if you are going to design an operating system, then you need to simulate it first. That how you simulate the scheduling first. That how your operating systems are which would behave in different situations. And if you are getting the optimum performance for that, then you will proceed with the implementation. Okay. So this is Dr. Rahul, and I was presenting chapter 5 of operating system concepts. It is the operating system course of Sukkur IBA and Computer Science Department. I wish you to see in the next section. Thank you.